Hello, dear friends. It's 9 o'clock, so we start our plenary session for Wednesday. And the first talk will be given by Maksud Ahmad Malik, the professor from Department of Chemistry, Jamia Millia Islamia Central University, India. With a talk multifunctional heterostructure-based nanocomposites for photocatalytic applications. Maksud, can you hear us?
Yeah, good morning. Yeah, can you hear me?
Yes, we hear you well, and we
Yeah,
see your
good morning to everyone.
we see your presentation. So you may start.
So, good morning to everyone. So, my talk is on the multifunctional heterostructure-based nanocomposites for photocatalytic applications. So, here we will discuss about the photo degradation application of these nanostructures. And first of all, why heterostructure-based nanomaterials? Why we choose heterostructures? So, as we know, heterostructures are composed of two different phases with different physicochemical properties. So heterostructure nanocomposites is composed of different phases. They give different electronic, optoelectronic properties because of the mixing of these two different phases. They show the this synergetic properties. So they can support each other's phase to uh, to make their properties better as compared to a single phase these materials. Uh, so they play a very important role in CO2 reduction, hydrogen production, some other biological applications. So how can we design them? The optimized ratio is important here. That plays an important role. You have to uh, put at some optimized ratio of different phases so that can alter the properties of these heterostructure nanocomposites. So uh, here, uh, how can you fabricate them? How the nanocomposites can be fabricated? So as we know, there are different methods of synthesis processes that include hydrothermal, microwave hydrothermal, sol gels, all these things. These are the methods how we can prepare these composites. But uh, the sequencing, how you can uh, synthesize our desired nanocomposites, because the understanding their mechanism of growth, mechanism there's a nucleation, and that's very important to understand the fabrication, to understand the development of the these heterostructure nanocomposites. So we discussed about the three different ways how we can synthesize these heterostructures. The first one is sequential stepwise growth of the sections of different materials. So here, what we can do is we can design in sequential way. First, one material will be designed, and over there will be another material will be designed. So in these materials, we have like core shell materials, we have multiple shell materials, and different branched materials that comes in this section. The another part in this another this way to develop these structures is direct growth of different building blocks. So we can directly grow them, nucleate them, and it's a very simple, straightforward method in this case. For usually used to fabricate the 2D nanomaterials, 2D heterostructures. And the third one here is concurrent growth of different parts through regulating the building blocks. So this method is used to fabricate the helical structures with uniform size and precise properties, because to control the size and the shape in the nanochemistry is an important factor to influence the the properties. Properties can be any photocatalytic, it could be the biological applications or any other applications. So uh, now, as my topic is on the photocatalytic applications, and we are talking about the photo degradation here. So photo degradation we are applying in water treatment, wastewater treatment. So as you know, the water crisis, they are increasing day by day all over the world, and so for that purpose, we have to design such catalysts that we can use that contaminated water to use in our daily life. So without, as you know, without water we cannot survive. And here you can see the stress, the water stress by countries by 2040. Most of the countries from here you can see from higher the ratio withdrawal ratio to the lower one. So the extreme higher levels you can find in the African, Asian countries, as well as Gulf countries, including like Qatar, Israel, Lebanon. They have a high stress of water in coming years. So there are a lot of problems they're facing. Like here you can see, according to the UN reports, we have 1.2 billion people who lack the access to the water every month. So 2.4 billion people suffer from contaminated water. That is the main our target, how to deal with this contaminated water. And it's because of the poor sanitations. So the drawbacks, the reason for this contaminated water is they cause deadly diseases like diarrhea, there, cholera, typhoid, and other hepatitis, liver diseases, which are all waterborne disease. So we have to we have to purify the released water, these because this waste, there are a lot of toxics in this water. So we have to purify the released water to control the water crisis. For that we have to build such type of systems, such materials that can be used to make this water uh, drinkable, so clean, so that the citrus, the problem which we are going to face in most of these countries in coming years can be rectified. Now, here we will discuss something about the water pollution and source of water pollution. So, uh, you have we have different sources where from we can have these pollutants coming. We have domestic releases. We have the contaminants coming from the chemical industries. The groundwater pollutants are there. Oil spillages are there. Like we know the nuclear wastages released to the water bodies, and thermal these pollution is there. So we use pesticides, like in our agricultural lands we use pesticides, fertilizers. They at the end come to the water bodies, which also contaminates the water. So we can say that the water pollution is an alarming condition, and the rate is going high. So, as you can see here in the slide, there are different sources of the the release source of water pollution. Uh, if we can clean this water and try to make it drinkable, lots of water crisis can be solved. So, for this purpose, so to we the scientists throughout the world, they are working on this developing such catalytic systems which we can use in sunlight, like the visible light, so that, and that should be in economical way also. So everybody cannot afford these systems. So the scientists are trying to develop every day different types of catalysts, where we can use these catalysts as a as a filtration source to clean this contaminated water. So So here, different types of nanostructures can be used. So here you can see in the slide that these water, the water coming, this wastewater, contaminated water, it passes through that photocatalytic reactors, uh, which have been irradiated by the visible light or UV light. It depends upon the light source, and we can get the clean water. So nowadays, many companies they are making such photocatalyst based these water filtration units where they coat their pipes, their transparent pipes coat with some photocatalysts. Particularly, you can see the TiO2 is used there, and irradiate them with some source of light or put them in under sunlight. So then and we can get the purified and clean drinkable water. So actually, the issue here is the solar energy, and it means that only the 5% of the solar energy it is about the UV light. So 43% is the visible light, and 52% is near the infrared. So here, main source of light is visible for us. So that is like we can avail anywhere of free of cost. So we need to design these catalysts according to their optical properties, which source of light they can absorb. So for that, so the we need to tune the properties of these materials. So these properties of materials can be tuned by tuning their size, shape, and their band gap. So, so band gap is also very important here, because we will only discuss here about the band gap tuning, because this band gap will allow you to use the source of light, what source of light you are using there, that will help you. So in the the band gap of the bulk materials, you can see here the bulk materials is less as compared to the when you the size is reduced, because the what is the size of this material is reduced from macro level to the micro level, and then to the nano level, the band gap increases. And the band gap, the spacing between the states get larger as the volume gets smaller. So why these nanomaterials behave strangely? Because electrons are squeezed, and and it is because of this quantum confinement. Quantum confinement, it is just like when you are squeezing some material and reducing its size from large to the smaller one. The electrons, they get confined to some particular like place, like a box. You have, and these confined electrons, and they have high energy. Their kinetic energy is increased. So that means the smaller the crystal size, and the higher the kinetic energy of these electrons. So here the important part of this property, tuning of this band gap property, is only to uh, to um, to reduce the size, and to change the shape of the material according to your desire, so that the particular wavelength, particular light irradiation can be absorbed by the materials. For example, we have a TiO2, titanium dioxide material is here. It's an indirect band gap material. It's a 3.2 electron volt. It's band gap. So the absorption edge of this TiO2 lies in UV region, which limits the catalysts in UV region utilization in larger wavelengths regions of electromagnetic spectrum. So, so how you can reduce the band gap of these small structures. So we use the impurities, which means that doping. We can dope with the metals, we can dope with the non-metals. So when you incorporate some metal dopants in the system of TiO2, the absorption edge, the visible light region of electromagnetic spectrum is extended, so leads to the energy reduction for the transition of electrons. So impurity creates impurity level is here. When you put some impurities on the surface of any heterostructure, any photocatalyst, it uh, it creates impurity levels near the top of the valence band and leads to the reduction of the band gap and alter the electrons charge transfer uh, directions. So under the influence of the visible light, the charge transfer of these TiO2 nanomaterials takes place from d electron state of metal impurity to the uh, to the Ti3D state, which dominates conduction band and leaving behind the holes. And so all these process from these bulk materials to the small materials is all about the band gap here. So here you can see the band gap is increasing, but we need the materials of the lower band gap where you can easily tune them according to their applications. One more example about this band gap is when you change the size, the size of the semiconductor, they can give you different colors also. That's also because of the absorption of light, what wavelength of the light they absorb, and what the energy the photons they emit. Accordingly, they will get the different colors of the semiconductors in the solutions. This also depends upon the absorption of the light. For that also, you need to tune its band gap. So here, one of the examples we can discuss is about the TiO2 doped with the nitrogen. So once you dope it with the nitrogen, it creates the new levels uh, under the valence under the valence band edges, above the valence band edges, new levels are created by which the electron excitation it becomes easy for the any material. So here also the quantum confinement and the quantum effect affects the band gaps also. Now here we are discussing a few examples of TiO2 doped. Here we have TiO2, we have this CO2 and SNO2 nanomaterial, this oxides. In the graph one here, you can see the number of shells, that the size of the material. What is the impact of the size of the material on the band gap here? So here we can discuss the nature of the dopant. So in the second plot here, you can see its dopant concentration versus the band gap. So what is the impact of the dopant concentration on the band gap? And here the plot one shows what is the uh, size of the dopant. As an example here, when the iron is doped on TiO2, Fe3 plus, its ionic radius is 0.64 angstrom. However, the size of this Ti4 is 0.68 angstrom. It means dopant ions has smaller ionic radius than host ions. So the material will have here the compressive strain on the materials. So uh, the size impact here will be shown on the band gap. Under similar conditions, when the dopant when the dopant concentration is changed, for example, you have the interaction between Ti3 and Fe3 ions. So the non-dopant, there is no magnetization, no free electrons are there, the unbalanced electron are there on the surface of you can find on the surface of these Ti2 nanomaterials. So when the material is doped with like cobalt, iron, manganese, and copper, you can see here the band gap varies. It's because of the interaction, the Ti3 ions interaction with the different these metal ions what we have doped on this on the surface. So in the same case, the comprehensive this strand will appear, and there will be exchange interaction between the Ti3 and as well as the Ti3 and Fe3 ions. So the band gap in that case will be reduced, as here curve 1 shows the lowest band gap as compared to the 4. That means 1 is for the cobalt, 2 is for the iron, 3 is for the manganese, and 4 is for the this copper. So in this TiO2 case, the valence band is dominated by uh, by oxygen 2p orbitals, and the conduction band is dominated by Ti3d state. When the metallic substituents impurity ions, you can say cations, integrate into the metal into the matrix of the TiO2 material, it created impurity levels near the top of the valence band. These oxygen vacancies, or you can say the point defects, play an important role uh, in uh, in in modifying energy levels of the conduction band. So here you can see TiO2 can absorb how these impurities, how these dopant concentrations, dopant types of the dopants affect the absorption of the light. So TiO2 cannot absorb visible light. So the total here, the major part of the light, we have the visible light. Due to its large band gap, it's about 3.31 or something is the band gap of TiO2. So that's why we reduce the band gap so that it come in the visible region. Now here, one more example, when the TiO2 photocatalysts were doped with some rare earth material, rare earth elements, so the band gap energy also uh, is reduced, it is coming down. So here in plot 3, this is dependence of band gap energy on the ion doping concentration in TiO2. We have here samarium, terbium, and europium. So these are the rare earth elements. So their size, the ionic radii of these rare earths is larger as compared to the Di ions. When you compare this with the iron doping, iron shows better effect on the band gap because of the tensile these tensile strains are there, so that the, the structure, the size of this materials, it is changed. So in conclusion, we can say here that the I will come to the conclusion of this tuning of the band gap here. So here, narrowing the optical band gap of TiO2, SNO2, and CO2 nanoparticles is essential for visible light applications. So when you compare with the transition metals and the rare earth dopings, the transition metals shows better effect on the band gap tuning of on the surface of the TiO2. So the uh, due to the different strands that appear on this TiO2, because of the different ionic radii of transition metals and rare earth ions on the host ion. Host ion means here the TiO2. So the impurities also here one more important effect of these impurities. These impurities also act as the electron traps for the valence band electrons, thereby diminishing the electron hole pair recombination. Under normal conditions, when you see the materials, when you irradiate them with some light, the photocatalytic activity is less due to the electron recombinations. Once the electrons are released, the holes are created and they come back and the recombination starts. So here, the impurities, whether they are transition metals here or they are non-metals or they are rare earths, so they stop this recombination. So after stopping this recombination, the generated exons migrate to the catalyst surface where they accelerate the redox reactions. So, how important is this band gap tuning for any photocatalyst design? So, our application here is regarding the photo degradation. So, here most of the textile industries, whether they are leather industries, rubber industries, printing, plastics, and the pharmaceutical industries, they are all the time busy releasing these dyes, toxics, these chemical, these wastes to the water. So our most of the water bodies nowadays, the rivers, they are full of these toxic materials, whether they are dyes, they are and there's some antibiotics. Like over the counter, you can get any antibiotic and you can use it and throw it. So the most of the water bodies are like contaminated. So they are not. We cannot use that water for drinking without purification. So for that, we need to design some balanced heterojunction photocatalysts here, so that they have a good stability, they have good applicability, they can absorb the the particular light source, and mostly it should be cheap catalyst, so that everyone can afford the use of these materials for the this wastewater treatment. Now here we have recently synthesized few heterostructures of alpha Fe2O3 and cerium oxide, and we deposit gold on their surface, and we test these materials for photodegradation of rose Bengal dye under visible light irradiation. And here we use hydrothermal method for the synthesis, and we use style trimethylammonium bromide as an ascorbic acid as a template and fuel for these materials. And here also we see one thing that once the heterostructure was created, there was some change in the band gap. On AU deposition, the gold deposition, we don't observe any structural deformation in and it was also observed through the XRD results that no structural deformation or no phase change was observed on deposition of gold on the surface of these Fe2O3 and CO2 heterostructure materials, and and the band gap was little bit reduced from 1.8 electron volt to 1.78. It was not that much because the band gap was already very low in this case, and the particle size was like about like 7 8 nanometers, in this case. So we use different scavenging materials to test the role of the different radicals which are responsible for the photodegradation. And here this is the mechanism of the materials. And we here the dye chosen was the rose bengal, and we approximately uh, 80, 85 percent of the dye was degraded in 120 minutes under the visible irradiations. For the second material we synthesized recently, it was the TiO2, and we loaded with the activated carbon. So activated carbon was prepared from the pistachio shells, and we burned these shells at 450 degree for 3 hours, and use that black powder, and we treated with the KOH and to activate it, and after that we calcine it for 800 degree cell at 800 degree cells for 3 hours. So this TiO2 powder, we use different loadings of this activated carbon with the TiO2, and we observed that this activated carbon was uh, uniformly dispersed on the surface of the TiO2. So the surface area of the activated carbon was about 375 meters square per gram. So as you know, the higher surface area and high pore volumes will facilitate the electrolyte diffusion through the pores, and can provide you the more space, more surface for the photocatalytic. So in this case, we choose one dye, and that's rose bengal, and we choose one drug, ofloxacin, for the degradation. And here you can see this is this rose bengal with BRTI2, this without the carbon, and the deposition of the carbon, this plot. And here this plot is with activated carbon TiO2 composite here, and you can see the degradation was fast. And in this case, this is ofloxacin with the beer uh, TiO2, pure TiO2, and here it was ofloxacin was degrading using UV light in presence of TiO2 deposited with activated carbon. Here also, the band gap uh, was reduced, the narrowed from 3.44 to 3.31 on deposition of the this activated 10% activated carbon. So which is different loadings here, and with this mapping, we can see here that the surface was the surface of the TiO2 was uniformly uh, dispersed with this. And here this is the mechanism, how the general mechanism for this. And the third example, we choose zinc ferrite, and we deposit this zinc ferrite with uh, copper. And we use here the green method. We use green co-precipitation method. Punica grantum flower extract was used to synthesize these materials. So uh, the size of Fe2O3 here was 15 nanometers. For zinc oxide, it was 29, and for zinc ferrite, it was 19 nanometers, and for uh, this copper deposited zinc ferrite, it was 16 nanometers. So the and the surface area increases from 30 for the pure Fe2O3, the surface area was 35.27%, this meter square per gram. For zinc, it was 25. For this zinc ferrite, it was 68. But when we deposit copper on the surface of this, there was a good increase in the surface area about 84.88 meters square per gram. So here also we observe some reduction in the band gap also. We find some reduction in the band gap from for pure Fe2O3 it was 1.65 electron volt, for zinc oxide it was 3.03, and when the zinc ferrite was formed it was 1.79, but when the copper was deposited on the surface it was about 1.63 electron volts. So here the band gap also plays an important role, and the size and the surface area of the material plays an important role for the degradation of rhodamine B dye here. So one different dye was used here for this purpose. In another case, we use Fe3O4 CDO nanocomposite for photocatalytic degradation of methylene blue here. In this case also, we observed there was the band gap for the pure Fe3O4 which was 1.9 electron volts. For cadmium oxide was 1.82. A slight decrease, the narrow in the band gap was observed after the heterojection was created between the two these oxides. So the combined we use here combined co-precipitation with the combustion method. So both co-precipitation and the combustion method was used for creation of these materials. And the morphology was a little better here. We find that these needle-shaped these Fe3O4 materials, and these are the dam images here you can see, and we find about 92% degradation rate in 120 minutes. The highest the degradation was achieved up to 92%. So this is the general mechanism of this photodegradation of methylene blue under this visible light radiations. So here, this is the general mechanism.
Maksud, sorry, only 2 minutes left of your talk.
Yes, please. So here, this is the general mechanism proposed here. The reaction of dye molecules on photocatalyst surface would be classified into the following categories according to the photocatalyst products. One is photodegradation, another is photodecolorization, photomineralization, and you have photodecomposition or photoexcitation. So these are the different processes what we have seen during these studies. So the first one, the photoexcitation, is when the TiO2 material is irradiated with light, so the electron and hole pairs are created. Then the ionization of water takes place uh, with the help of the irradiated light. You get OH radicals, and then in the third step, the oxygen, the surface or the oxygen available there, it reacts with the electrons in the conduction band, and you get the peroxide radicals. And all these radicals, they are important. They play an important role in the degradation of any pollutant, or whether they are the bacteria present in the water, the dyes are there, the drugs, the antibiotics or other drugs are there. These radicals, they play an important role in the degradation process or decolorization process. But here, one important thing is the decolorization means the color it can come back also. So this is the general mechanism here shown. So we are here short of time, and my time is over now. And I appreciate your patience and listening this talk. And thank you very much.
Let's thank the speaker. Please. And now your questions.
Thank you very much for your very interesting talk. Would be possible to compare efficiency of photocatalytic systems based on oxides with efficiency of photocatalytic systems based on halcogenides of transition metals, please?
your question is about the deposition of the transition metals on the surface, the doping of the transition metals?
Yes, using of chalcogenides of transition
Yeah.
metals and photocatalytic systems based on chalcogenides of transition metals.
Will you please repeat your question? Your voice is not clear to me.
Okay. Would be possible to compare efficiency of photocatalytical systems based on oxides with efficiency of photocatalytic systems based on chalcogenides of transition metals?
Metals, as I discussed here, they play an important role because of their ionic size, and it depends upon the size difference, the lattice parameters. When there is a difference in the lattice parameters of the systems, whether the host material and the dopant material, that plays an important role, the strain, because there could be the deformation of the size also. The structural deformation can take place, but we can the strain. The tensile strain can take place. So that plays an important role there. So it depends upon the type of material you are doping and its compatibility with the ionic radius, the size of the host material and the dopant this material. Accordingly, you can say whether it is better photocatalytic material or not. And also, as we see here, which material, as we can say the non-metals in some cases, for example, if you dope nitrogen on the surface of TiO2, it gives better effects as compared to the transition metals. And that is about the size compatibility of these materials on the near the ions near the valence band and the conduction band, and that will definitely impact their photocatalytic activities.
Thank you.
So let's thank the speaker, and due to time frames we have to move faster. And the second speaker today is Professor Mohammad Sahid Khan of Department of Physics, Jamia Millia Islamia, Central University, India, with the talk Functionalized Quantum Dots for Solid State Lighting. Mohammad, are you here? We see your presentation, but we can't hear you.
Can you hear me, Professor?
Yes, now we can hear you well. So you may start.
Okay. Okay, a very good morning to all present here. And I take this opportunity to express my sincere thanks for the organizer to give me this opportunity to present this talk in this 10th edition of the ITNT-2024. I'm currently working as professor in the Department of Physics, Central University, Jamia Millia Islamia, situated in New Delhi. Here is the outline of my talk titled Functionalize Quantum Dots for Solid State Lighting, starting with the introduction comprising of the need for luminescent materials for lighting and including the challenges and goals in developing quantum dot-based phosphors for lighting devices. I'll discuss the results of our continuing endeavor to develop functionalized quantum dots suitable as phosphors for solid-state lighting devices, followed by a quick summary and acknowledgements. Luminescent materials, commonly referred to as phosphors, have the ability to absorb energy from incoming radiation and then re-emit light. In recent years, luminescent materials have found widespread use in variety of fields. Major population applications comprise emissive displays and lighting devices like white LEDs, solar cells, lasers, and amplifiers in optical communications. The light emitting diodes are becoming more and more important as the demand for energy conservation is increasing day by day. The harm that traditional lighting sources cause to the environment and to the pupil's health only increase this demand. The evolution of lighting sources started with the advent of the incandescent lamps. The important parameter about the lighting source is the luminous efficacy, which is the uh, amount of visible light emitted for a given amount of electrical power consumed. As we can see from here, the incandescent lamps luminous efficacy could not be increased beyond about 40 lumen per watt. Then came these fluorescent lamps, and we can see that their luminous efficacy could be increased up to 100 lumen per watt. After that, the LEDs came into picture, and one can see that from this diagram that their luminous efficacy increases in leaps and bounds very quickly, and the LEDs offering luminous efficacy of the order of roughly 75 lumen per watt were reported. Very recently, Gao et al. In 2016 reported light emitting a white LED based on quantum dots phosphors with a luminous efficacy of about this dot basically represent that work reported in 2016 having luminous efficacy of around 121. More recently in 2022, Zhang et al. Reported white LED, white light emitting diodes having a luminous efficacy of 127 lumen per watt. Although this light of different colors can be produced by the LEDs, but one of the fundamental limitation of the LED is its sort of low or narrow bandwidth in which the light emitted from it can be thought of as if it is monochromatic in nature. That means it has a small bandwidth. So that any LED giving any light cannot be directly used as a source of white light, which is so important for illumination purposes. This issue can be solved by combining light of three colors, for example, red, green, and blue, from three different LEDs. But different LEDs have different luminous efficiencies or efficacy. Therefore, this solution become quite impractical. Therefore, the usual technique of generating white light is to combine blue light or near ultraviolet light from some LED, blue chip LED, and coated that over with some phosphor or luminescent material like yellow phosphorus, so that the resultant output is the white light. So one can have this chromatic source, a different kind of dichromatic, trichromatic source, etc. So one can have, for example, ultraviolet LED with some red, blue, green phosphor together, or yellow phosphor that will give you white LED. So one basically requires phosphors. Phosphors are the materials that have ability to absorb the high energy light emitted by some LED chip and down convert that into a lower energy or in the some other range of the visible spectrum. So the ideal answer to this problem that one cannot directly combine this three different colors light, red, blue, and green, from different LEDs is provided by this phosphor material. A schematic is shown here for the device which can be used as a white LED. So one has this, for example, LED based on indium gallium nitride chip emitting blue light and a yellow phosphor. Okay, the resultant is the blue light. So this curve shows this the overlapping of this mixing of these blue emission from a LED and this yellow phosphor emission from a phosphor material. The resultant is this total white emission. Again, there is a problem here, as one can see that the relative intensity in this blue-green region is low as compared to if one compare this emission spectrum of this white LED with that of sunlight, diffuse sunlight, one can see that the relative intensity is quite high for the entire visible region, especially in the blue green region. So there is a need to develop phosphor materials, but any phosphor material cannot be used directly unless it satisfies certain criterion. Uh, the foremost one is the favorable luminance characteristics, like having exceptional quantum efficiency, exceptional very stable fluorescence at even high temperature, significant absorption in the near ultraviolet and blue spectral ranges, and short emission decay time. All these luminance characteristics serve as the initial screening uh, criterion for any material to be used as a phosphor in a phosphor converted white light LED. The second important criterion for any material to fulfill in order to be used it as a phosphor material is enduring stability, as as the stability of this phosphor material affects the durability of uh, the PC converted white LED itself. Another another important criterion for a material is that it should involve less cost and minimal use of resources, because we are now in a era where we are looking for more and more solid state lighting, but the cost is an important criterion. Therefore, any phosphor involving high cost is not a desirable material. So from the standpoint of the phosphor developer, the entire affirmation requirement should be satisfied by making improvements in two areas: lowering the cost of processing and raw materials, and lowering the mass of phosphor needed in the PC converted phosphor converted LED package in order to meet the intended color specification. And there is one more requirement that any phosphor material should fulfill, is that it should be environmental friendly, so that it can contribute to the sustainable development of our world, especially uh, to discover phosphor for lighting, uh, which are suitable for as fluorescent material and can be used for solid state lighting devices. The usual technique or practice is to incorporate the transition metals and rare earth into the host materials. But involvement of these transition metals and rare earth host materials requires chemical processing and processing that leads to the increase in the cost of these material, ultimately increasing the production cost of the material for the white light emitting devices or diodes. Therefore, we always want to avoid these, involvement of these, especially rare earths host into the phosphorant material. The answer to this problem is provided by quantum dots. Quantum dots are basically stable semiconductor nanocrystals having a size usually less than 10 nanometer. The quantum dots are usually composed of a metallite crystallite core, uh, okay, so that it becomes it metallite core and follow, which is in encapsulated in by some shell. So this basically provides the stability to the structure, as well as it also gives stable or lead to stable photoluminescence. Quantum dots can be made of several elements from group of elements in the periodic table, like second, sixth, third, fifth, and so on. So, also, the single element quantum dots can also be synthesized, like carbon quantum dots, graphene quantum dots, and silicon quantum dots, etc. Due to size quantization effects, quantum dot exhibit very unique and peculiar optical characteristic which resembles the optical characteristic of atoms. As quantum shrink in as quantum dot size shrink, the electron becomes more tightly constrained, causing an increase in the energy gap that leads to the decrease in the wavelength of the emission. Okay, so one can see that the same material, the quantum dots of the same material can be used to have the emit different colors of the light emitted from the same material, but having different size of the quantum dots. The Although despite the quantum dots have been used as a promising material for numerous prospective application due to their exceptional structural qualities, but the quantum dot research is still in its early stages, and there are some problems and difficulties that need to be overcome in order to fulfill the expectation of future. Some of them are listed here. The regulated and extensive synthesis of quantum dots with predetermined characteristic remains difficult. In order to fulfill the requirement in the lighting industry, the extension of color tunability in the visible NIA region, as well as controlling the intensity of the photoluminescence from these phosphor element is still crucial. Achieving high photoluminescence quantum yield is a major difficulty. And of course, another concern is that of synthesizing quantum dot using more environmental friendly method for lowering the toxicity of heavy metals based quantum dots. So the goal of major current research in the area of quantum dot based phosphor is to develop more phosphors and study their uh, luminescent and structural properties, examining the origin of the photoluminescence in the quantum dots, and tuning the photoluminescence emission of these quantum dots by functionalizing or with the dopants. uh, Improving the key parameters, uh, defining the the light quality that one gets from these phosphor converted LEDs is very important. For example, this CRI value, which is color rendering index, CCT, color correlated temperature, color purity, and luminous efficiency is so we are interested in developing these phosphors, quantum dot based phosphors, so which have these high value of these parameter, color rendering index, CCT, etc., so that they fulfill the requirement of a suitable phosphor as we discussed earlier. The So as part of our research endeavors to develop quantum dot based phosphors, we worked on the synthesis of uh, functionalized carbon quantum dot using a simple hydrothermal method using a very low cost precursor gelatin. Uh, and and we were able to synthesize carbon quantum dot which were found to be rich in nitrogen. The time analysis confirmed the formation of the carbon quantum dots having a mean diameter of the size of 2 to 2.5 nanometers. The X-ray XRD pattern confirmed the amorphous nature of the as synthesized carbon quantum dots. The entire spectrum revealed the presence of number of important functional group like amide, hydroxyl, carbonyl group, etc., which were further confirmed with uh, the presence of these functional group were further reconfirmed from the XPS spectrum. As one can see from here, the presence of these important functional group on the surface of the carbon quantum dot was recorded in complete XPS spectra. The UV visible absorption spectrum revealed a broad absorption peak in the range of 250 to 290 nanometer, and the this carbon quantum dot prepared carbon quantum dot revealed a blue emission when illuminated in the ultraviolet light. The CI graph was plotted for the this blue emission, and its dominant wavelength was found to have a CI coordinate of 0.17, 0.14, showing that it has an emission in the blue region of this CI diagram. These as prepared carbon quantum dots exhibited excitation dependent fluorescence emission. Uh, the PL emission spectra were recorded for different excitation wavelength ranging from 280 nanometer to 420 nanometer, and it was found that the emission intensity can be controlled was dependent on the excitation spectrum. The maximum luminous intensity was observed for the emission spectrum, which was obtained at the excitation of 340 nanometer wavelength. The time correlated single photon counting experiment was performed to uh, to measure the fluorescence lifetime, and the as synthesized carbon quantum dot were found to have a average lifetime of 3.3 nanosecond, which fulfills the minimum criterion of fast decay mechanism present in the any phosphor material to be used as a phosphor in any lighting device. The quantum yield of this carbon quantum was also found to be 22.7 when compared with the reference quantum yield of the reference compound rhodamine B. Uh, it was found that we were able to synthesize these carbon quantum dots using a simple hydrothermal method requiring no chemical processing or the purification, and the size and the quantum yield of our carbon quantum dot produced was found to be comparable to these parameter reported earlier. In order to improve the luminescent property of these materials, carbon quantum dots, we synthesize the carbon quantum dots and doped these carbon quantum dots with copper and manganese. The Again following the hydrothermal method of synthesis. We basically prepared two samples, one undoped carbon quantum dots and other one as the uh, carbon quantum dot which was co-doped with copper and manganese. The typical HRTEM images showed that the mean diameter of this undoped carbon quantum dot was around 6 nanometer. On the other hand, the doped carbon quantum dot had a mean diameter of 5.5 nanometer. The XPS spectra again revealed the presence of number of functional group which are very important for tuning the photoluminescence, as we will just see in our photoluminescence spectra. The presence of these different functional group like OH, C double bond, OCN, amide group, and carbonyl group, etc., were reconfirmed with the record of the FTIR spectrum. And the in addition to these functional group, the FTIR spectra of the doped carbon quantum dot, which is shown here by the red curve, showed two additional peaks at 664 centimeter inwards, corresponding to manganese oxygen stretching vibration, and another one at 513 centimeter inwards here, corresponding to copper oxygen stretching vibration. The the UV visible spectrum of the undoped carbon quantum dot exhibited a broad peak centered at 227 nanometer which we could assign to pi state transition in the sp2 core of the carbon quantum dots. This band was found to be redshifted in case of the copper manganese core of carbon quantum dots, and was it was found to be centered at 336 nanometer, and this was assigned to a transition from n to pi star transition of the surface functional group, which were found on the surface of the carbon quantum dots. So here we show the possible mechanism. The presence of the number of functional group on the surface of the doped carbon quantum group provided different possible relaxation pathways. So presence of these functional group lead to the formation of the new energy state, like a non-bonding energy state corresponding to oxygen and nitrogen above the pi state of the system, as well as the surface defects leading to oxygen related states and the nitrogen rate. This provided other possible relaxation mechanism for the system, and therefore what we have actually is this: if we excite these doped carbon quantum dots, the emission we can get different emission, as there are various possibilities of relaxation mechanism. So there is a possibility that this doped carbon quantum dot can be excited with this much energy, and leading that will ultimately lead to the emission, this emission was characterized by drawing the CI diagram of the emitted light from these doped and undoped carbon quantum dots when they were excited at different excitation wavelength of starting from 280 nanometer to 380 nanometer. The undoped carbon quantum dot emitted a blue light with the CI coordinator falling in the blue region of the CI diagram. On the other hand, when these doped carbon quantum dots were excited with the other wavelength like 320 nanometer, 340 nanometer light, etc., the emission shifted to the orange and red region of the CI diagram. That means the emitted light was orange or red emitted region. So it means it is possible to tune the wavelength of the emitted light from this carbon quantum with the use of a different excitation wavelength. Of importance is this second this CI coordinate plotted here by this square, designated as second, which correspond to the emitted light obtained from this doped carbon quantum dots when excited with 300 nanometer. This lies in the region of white light emission, okay, which is shown here in the diagram. So the CI parameters of this copper manganese doped carbon quantum dots under different excitation, and one can see that the emission becomes white from one single phosphor itself, and it has a CI XY coordinate of 0.36 and 0.30, which are close to 0.33, which is for the dominant wavelength of the perfect white light. The color rendering index is for this doped carbon quantum dots when excited with 300 nanometer wavelength. Light is found to be 89, which is close to the required value of 90, minimum value of 90 CRI, color rendering index. CCT, color correlated temperature, is found to be that of 4000 K, and luminous efficiency was calculated to be 29. It is found that the photoluminescence quantum yield of the pure carbon quantum dots increases to around 28, 29% from that of the 11%. These CI parameters are basically suitable uh, for the lighting purposes, that this one single uh, copper manganese doped carbon quantum dot can be used as a phosphor of different color when excited with different wavelength, and can also itself use as a white light emitter when excited at 300 nanometer light. So we basically found that this copper manganese doped carbon quantum dots has this outstanding color properties, which is suitable for indoor lighting. In another work, we studied and synthesized the manganese and europium dot zinc sulfide carbon quantum dots to study it as a phosphor material. We kept the doping of manganese to 2%, while we changed the percentage of doping of the europium from 0 to 4% using the co-precipitation method. The XRD and FTIR spectrum confirm the formations or synthesis of the zinc sulfide quantum dot using the standard techniques, and we found that there was no deformation of the XRD or FTIR pattern, except slight shifting was observed in case of the doped zinc sulfide quantum dots, confirming that the dopant ions manganese and the europium has been successfully incorporated in the zinc sulfide host. Uh, the TEM uh, TEM micrograph revealed the mean diameter of the undoped to be of the order of, whereas the doped zinc sulfide quantum dot had the average size of the 1.8 nanometer, uh, confirming the successful formation of the quantum dots of the doped and undoped zinc sulfide. The X-phase spectra again confirmed the elemental percentages of the different elements as per our synthesis protocol. No impurity was were found in this X-phase spectra. The uh, the UV visible spectrum also revealed that there is a small shift in this dominant peak at the observed at around 4 nanometer in case of the doped zinc sulfide quantum dot as compared with this undoped zinc sulfide quantum dot. Uh, special important to us was the emission PL spectra of the as prepared quantum dots. Uh, so we found that this black curve denotes the PL spectrum of the undoped zinc sulfide. On the other hand, with the incorporation of manganese in the zinc sulfide quantum dots leads to the emergence of a new peak in this PL emission spectrum centered about 600 nanometer, whose intensity was found to increase with the further incorporation of European 3 plus ion doping of 2%, and which was further increased with the increase in the doping of the European 3 plus ion in to 4%. The PL quantum wheel was found to increase again with the increase in the dopant percentage. And this diagram schematically present the origin of the photoluminescence spectral transitions, and one can see that the zinc sulfide, which is itself zinc sulfide quantum dot, which is itself is a blue emitter, but with the incorporation of the manganese in the zinc sulfide lattice, the new energy states are evolved, which are linked to the manganese ion, and therefore leading to the decrease in the energy gap that leads to the emission of the light in the orange color. Incorporation of the europium 3 plus ion in the zinc sulfide lattice leads to the presence of surface vacancies, and thereby we find that this is possible to have the orange red emission from these doped zinc sulfide quantum dots. We can see that from this CI diagram plotted for the PL emission, that this pure or undoped zinc sulfide
Dear Muhammad, sorry we can't hear you, and also only 3 minutes of your talk.
of these manganese and the uranium, we can tune the emission obtained from this zinc sulfide quantum dot, okay, and that opens up a new avenue for the promising application of the doped quantum dots in white light LEDs. So we were able to synthesize these zinc sulfide quantum dots and tune its color, emitted color, by doping these ions into the lattice. Very quickly, I would give the as I discussed, that this involvement of rare earth is a costly affair. Okay. So to avoid these rare earth incorporation, we synthesize these zinc sulfide quantum dots with and dope them with cobalt and silver. The as prepared zinc sulfide quantum dots undoped were found to have a mean diameter of 6.5 roughly nanometer, and the mean diameter of this zinc sulfide quantum dot doped with cobalt, as well as cobalt and silver, were found to have the value of 6.7 nanometer and 7.11 nanometer, fulfilling the criterion to be called the quantum dots. The XRD and FTIR spectra confirm the formation of these quantum dots, that the incorporation of these dopant ions was successfully done without changing the basic lattice parameter of these zinc sulfide quantum dots. Express spectra was also recorded, and that gave us the elemental percentages of the different elements in our quantum dots. The UV visible spectra recorded was show that without the inclusion of cobalt and silver ions, the broad absorption was observed centered around 280 nanometer. On the other hand, there was a shift in this dominant absorption peak towards right side with the incorporation of the cobalt or cobalt silver doping. Again, the of importance to us was the emission spectrum, which we from where we noticed that this black curve is the PL spectrum of the undoped zinc sulfide, but has no emission here is in the red region, but with the incorporation of the cobalt, new peak emerged centered about 620 nanometer, which further got enhanced with the co-doping of the zinc sulfide quantum dots by cobalt and silver. So we found that by drawing
Muhammad, sorry, but the time of your talk is almost finished. Please.
Just 2 minutes. This is my last
conclusion.
Yeah, it is. This is the second last slide. Okay. So with this incorporation of the cobalt and the cobalt silver co-doping of zinc sulfide, it is possible to tune the emission color of the quantum dots from blue to this red emission or to the reddish orange emission. So we found that these doped cobalt and cobalt silver co-doped zinc sulfide quantum dot has a CCT value of less than 2000, which are suitable for the warm cooling, warm lighting applications, and the purity of these emitted light was also quite high, of the order of roughly 90%. So here is the summary, is that it is possible to tune the photoluminescence or the photoluminescence of the doped carbon quantum dots, and even multicolor emission can be obtained from doped carbon quantum dots. And at a particular emission, this doped carbon quantum dots can be used as a single phosphor for white light, having suitable CRI values of 89 CI coordinates, very close to the coordinate of the white light, and a CCT value of 4000, meeting the needs of all indoor lighting. In the second part, we basically discussed that it is possible to tune the emission spectrum of the zinc sulfide quantum dots by co-doping it with cobalt and silver. So finally, the acknowledgement, especially my former research scholars, Urusal Latif and Shafiul Islam, who worked extensively on this work, and my other collaborator from my university and some other university. And finally, big thank you to you for giving me a patience listening. Thank you very much.
Thank you for the amazing talk. Yes, let's thank the speaker. Your questions, please. Any? If so, I have one practical question. Please, may you tell us what gaps must be eliminated to push the techniques, the methodology that you presented to us right into the field?
Please repeat your question. What should be removed?
My question is about the practical implementation. What gaps still
Right.
must be eliminated to push it into the industry?
What impetus?
Excuse me?
So actually, our endeavor is to develop these phosphors so that they fulfill the requirement of the criterion which industry requires. So for this, basically, there should be sufficient quantum yield so that this can be used for the industrial manufacturing.
Okay, thank you. Once again, thanks for your talk. Let's thank the speaker one more time. And we move further. And the next speaker will be Professor Alexey Zhukov, the corresponding member of Russian Academy of Sciences, professor of Higher School of Economics University, the St. Petersburg branch, with the talk Quantum Dots, QD lasers, and micro lasers.
Yes, thank you very much for the introduction. Can you hear me well? Yes. Okay. Most of all, and first of all, I would like to thank the organizers for invitation, and personally, academician Sofer. So I have an opportunity today to deliver my presentation. But I would like to ask the chairman whether our foreign friends still with us online. So can I change my presentation to Russian? If you don't mind. So, it will be a little bit more convenient for me and for the audience because I can provide more information as I can for the time is limited. So you can say, well, once again, talking about quantum dots, but I will say about some other sorts of quantum dots, about quantum dots which can be grown epitaxially, and because of this, they can be inserted into the semiconductor matrix and can be injected by electricity. So it gives additional flexibility and additional opportunity for the application. Let me continue my introduction. Yes, first of all, I would like to say that I have little knowledge about the economy, but still work in the high school of economics. But as some people say, HSC University means high school of everything, not just high school of economics. And also, I was attracted by the HSC to establish a physical department in St. Petersburg branch of HSC University. So for the last 5 years, my main affiliation is HSC University, where we established the laboratory, and I will present the results achieved by our laboratory in collaboration with some other colleagues from Russian institutions, from foreign institutes. I will show a little bit later. Yes. Maybe a few words about myself. I started my academic career in the York Institute, and the main achievements here in our MBE group, it was a demonstration of the first in the world quantum dot lasers, and quite soon we demonstrated the first quantum dot vertical cavity surface emitting laser. After this, I moved to the Alfyorov University. In that time, it was just St. Petersburg University of Physics and Technology of the Russian Academy of Science. And here we still focus on quantum dots and their application for lasers. And for example, we demonstrated in that time first quantum dot microdisk lasers capable of operating at elevated temperature as high as 100 degrees C, which is the world record at that moment. Also, we start activity with quantum dot microdisk lasers grown on a silicon substrate, and demonstrated the first CW operating quantum dot microdisk lasers on silicon. And as I said, 5 years ago, I moved to the HSC University, and we continue activity there, and mostly devoted to application of quantum dot and quantum dot lasers for optical communication, for sensing, and so on and so on. So in my talk, definitely we base on some previous background, and St. Petersburg, Leningrad are quite famous for their scientists. I tried to collect in this slide those who worked in St. Petersburg and Leningrad, and are the Nobel Prize winners. And among these persons, these gentlemen, I would like to pay your attention to, first of all, Professor Alexei Yakimov and academician Jeres Arfilov, because their invention are in very close connection with the topic of my today's presentation. So we already know some basic information about quantum dots, and usually when people say about quantum dots, they talk about possibility to change the emission or absorption wavelengths, changing the size of quantum dots. But the same can be done using two-dimensional quantum wells. So what's the advantage of quantum dots? I would say that compared to two-dimensional quantum dots can extend the operation wavelength range compared to the same structures with two-dimensional covering. For example, in case of gallium arsenide substrate, indium gallium arsenide quantum well can reach the wavelengths of only 1.1 micrometer, which is not enough, for example, for optical fiber communication. Using quantum dots, one can grow lasers on the same gallium arsenide substrate, but the wavelengths can be shifted to 1.3 micrometer, which corresponds to the zero chromatic dispersion of conventional single-mode fiber. Also, because of quantum dots are small compared to two-dimensional quantum well, they can use other materials with higher lattice mismatch, for example, compared to quantum well. This gives additional flexibility in choosing the materials and their optimization for different purposes. And also, especially for laser application, it is important that quantum dots usually have quite low surface density. So it's more easy compared to two-dimensional quantum well to excite quantum dots and make them to provide gain for lasing, because to estimate how many current density is required to be applied for lasing is just can be calculated like surface density of quantum dots multiplied by the electron charge and divided by luminescence time. So the lower surface density of quantum dots, the easy to achieve lasing. And well, the last but not the least advantage of quantum dots is very high expected temperature stability because of deep localization of charge carriers inside quantum dots. And here I demonstrate some theoretical prediction made already 40 years ago about quantum dot lasers, which could be very stable against temperature. So the threshold current density should be absolutely stable, while the other sorts of active region demonstrate more or less high temperature sensitivity. If quantum dots are so attractive, how to fabricate them? The first sort of quantum dots was small crystalline particles made in a glass matrix after some annealing process. So that's exactly what Alexei Yakimov demonstrated in the beginning of 80s, jointly with his colleagues from GOI Institute. So they demonstrated the absorption lines and the position, spectral position of these lines exactly corresponds to the size of the particles. So they demonstrated that this is indeed a quantum size effect. But this sort of quantum dots located in a glass are not suitable for electrical injection, and this is also just absorption, not light emission. How to fabricate light emitting quantum dots? So there was a thought to make etching by semiconductor structure, but the small size of etched areas prevent emission because of different defects, and also the size distribution are quite large. So suddenly it was found that quantum dots can be fabricated by so-called self-organization process. So no external force is required to fabricate quantum dots, just because of some internal processes during the epitaxial growth, a thin two-dimensional film redistributed into an array of islands. And these islands can be considered as an array of quantum dots because their size are quite small. Typically, the size is just a few tenths of angstrom, a few nanometers. So it's maybe one of the first transmission electron microscopy image of a quantum dot array, which was fabricated non-intentionally because these people try to make digital alloy, so-called digital alloy, not just indium-gallium arsenide, but indium arsenide, gallium arsenide superlaser. And then they found that when the thickness, effective thickness of indium arsenide exceeds certain critical layer thickness, two-dimensional film transforms into an array of quantum dots. And after that, demonstrated that if the thickness kept quite small, the efficiency of light emission from quantum dots are comparable to two-dimensional quantum dots. And what we did immediately, we put these self-organized quantum dots inside the injection diode laser epitaxial structure. So what we changed, we just removed two-dimensional quantum well and fabricated quantum dot inside. And we observed lasing emission from to zero-dimensional states. For sure, this sort of quantum dot lasers, the first one was very far from the theoretically predicted advantages because the threshold current density was quite high and temperature stability was poor, and it took many years for improvement of the quantum dot characteristics. Maybe one of the most important things what was invented in the field of quantum dots, it was a demonstration how to change the wavelengths of emission of quantum dots. If we just fabricate quantum dots by depositing indium arsenide, the wavelength is maybe 1.2 micrometers and not longer. If we try to add more material, the dislocation formation takes place and the emission efficiency drops significantly. But if we need to achieve a longer wavelength emission, it was very simple method. We can cover indium arsenide quantum dots with a low bandgap material like indium gallium arsenide. So the so-called quantum dot in a quantum well. So quantum well provides additional tunability of the quantum dot emission. Quantum dot can be fabricated in the optimal regimes, for example, to achieve better size distribution, uniformity, and so on, and changing the thickness and the composition of indium gallium arsenide capping quantum well, one can change the emission. And what is more important, in addition to the 1.3 micrometer is suitable for fiber optic communication, is that this sort of quantum dots provide very deep localization of electron and holes inside the active region. So it's very difficult or maybe even impossible for charge carriers be thermally activated from the quantum dots to the matrix, and as a result of this, these sorts of quantum dots are very stable against, or for example, temperature variation or some sorts of defects and so on and so on. And we will discuss this a little bit later. Another important invention was a demonstration that quantum dot can be stacked several times. So we can use not just one plane of quantum dot, but we can stack as many as we want depending on certain application. For example, if we want to achieve very low current density, it is better to use just one plane of quantum dots. But if we need to increase optical gain, for example, to provide more optical power, or if we want to use quantum dots as for detection light, it is better to have many planes of quantum dots. So the secret, the trick is to use so-called spacer between planes of quantum dots. Spacer is a material which is unstrained, for example, the same gallium arsenide as the substrate, or aluminum gallium arsenide, which has the same latest parameter with the same as gallium arsenide. So if we need to use many planes of quantum dots, we should separate them with sufficiently thick spacer layers. What else? It was found already maybe 20 years ago that quantum dot lasers are unpredictably stable against, for example, deep etching. So typically semiconductor materials are very sensitive to surface combination because free surface is always full of some absorbed atoms, some traps, and so on and so on. And all these traps acts as a deep levels, which leads to non-radiative recombination, like the same as the deep levels in the bulk materials. But this is not the case for quantum dots. And the reason was found. It's very simple, because electrons and holes are localized and spatially localized inside quantum dots. So they have very little probability to move to this surface and recombine there non-radiatively. Electrons and holes are located inside quantum dots in the body of the laser structure, but not in their surface. That's why quantum dot heterostructure can be etched very deeply, and this gives some additional flexibility, for example, for fabricating some complicated structure like microdisk, microring, some waveguides where very narrow stripes are required, some to waveguide light. Now I just briefly demonstrate you some recent or already not very recent achievements in field of quantum dot lasers, and maybe the most brilliant one is the demonstration that indeed threshold current density of quantum dot lasers can be unpredictably low. Just 10 amps per square centimeter is required to achieve lasering at room temperature. This is exactly what is expected from the theoretical viewpoint. If we calculate the current density required to achieve inversion population in quantum dot array, it would be approximately 10 amps per square centimeter. So this means that no additional ways for charge carrier recombination, no non-radiative recombination inside, no radiative recombination on the side walls, for example. So it's everything works ideally as expected for ideal quantum dot array. So here is some historical diagram which demonstrating how the threshold current density of diode lasers improves from time to time, from in accordance with their development. So when the two-dimensional quantum well lasers was initially demonstrated, their threshold current density was much higher compared to conventional for that time bulk material laser. But because of a potential in the quantum well, because of they provide better carrier localization, for example, and some other advantages, the threshold current density soon reach the levels of approximately 50 amps per square centimeter, whereas the bulky materials cannot give the threshold current density lower than maybe 500 amps per square centimeter. The same story was with the quantum dot. When quantum dot lasers was first demonstrated, the threshold current density was much higher compared to the quantum well counterpart. But quite soon, because of some improvements, deeper localization of charge carriers, because of using stacked arrays of quantum dots, improving epitaxial technology, the threshold current density drops to the level well below the quantum well limit, maybe 5 or 6 times lower. Also, it was a very significant, very strong discussion in the field of quantum dot laser, how they stable against temporal degradation, because quantum dots are material which is strained inside the semiconductor matrix, and so it could be some induced by temperature or induced by current flow degradation of their characteristic, but upon a certain time of development, it was demonstrated that quantum dot laser can be very stable. For example, the estimated lifetime is as long as 1 million hours. This is more than 100 years. So this time corresponds to the degradation of the operation power by 20% during this period. And I would like to mention that not only quantum dots grown on native, for example, gallium arsenide substrates are so stable, but recently it was demonstrated that even quantum dot laser grown on non-parent substrates, for example, on silicon, also can demonstrate very long lifetimes. This is for example, was demonstrated in this work where the lifetime was estimated as high as 100,000 hours. Another example of very high temperature stability of quantum dot laser. So the maximum operating temperature exceeds 200 degrees C. So it is more than required for any practical application, because typically people consider it application of lasers at elevated temperature, and the elevated temperature means usually 85 degrees C or something like this. Also, I would like to say that typically when people talk about lasers, they want to have very narrow emission lines, as narrow as possible. But sometimes the broad emission spectrum is required. For example, it is required, for example, for tunable laser, because it's very convenient to have one diode which is capable of providing wavelengths which can be intentionally changed in a very broad range. So quantum dots, because of some distribution of their size, can provide broad gain spectrum. And then the gain spectrum can be additionally extended by using, for example, deposition of several planes of quantum dots with slightly different parameter. As I said, quantum dots are kept with quantum well, and this keeping quantum well can be changed from layer to layer. For example, the thickness of this quantum well can be changed gradually, so the gain spectrum will be additionally broad. And this gives a chance to reach very broad gain spectrum, more than 100 nanometers broad. Also, in the Fabry-Perot lasers, when they know spectral selections, very broad emission spectrum comprising many Fabry-Perot modes can be achieved. These Fabry-Perot modes can be spectrally selected and used as a separate optical channel, and this was demonstrated. Well, if spectrally selective element is inserted to the laser cavity, for example, DFB, distributed Bragg refractor, are used, or distributed feedback is used, quantum dot lasers are capable of providing very narrow emission line, a single frequency operation. And what is more important, the frequency operation, single frequency operation, is associated with very high output power and reasonable power conversion efficiency. So the power remains high even at elevated temperature, and the power conversion efficiency also remains high even if the temperature exceeds 100 degrees C. This is quite unusual for quantum well laser, for example, for indium phosphide-based quantum well lasers, which is the most counterpart for quantum dots lasers in the spectral range of 1.3 micrometer. Because in indium phosphide materials, the band gap offsets are typically not very large. So the increase of temperature results in very strong carrier escape from the active region. And this is just to confirm my words that very record small wavelengths, line widths can be achieved using single frequency quantum dot lasers. This is because in semiconductor laser, the line width is typically limited by so-called alpha factor or Henry factor. And this alpha factor depends on the shape of the gain spectrum. In a quantum well, the gain spectrum is asymmetric. So, and because of Kramers-Kronig relation, when the gain change, this results in changing the refractive index, and this change of refractive index leads to additional broadening the emission line. So in the case of a quantum dot, the gain spectrum more or less Gaussian, and if lasing proceeds in the top of this Gaussian distribution, the alpha factor could be exactly zero. So in practice, of course, the alpha factor is not exactly zero, but very small. For example, less than 1. So this gives advantage to quantum dots for achieving low lines in single frequency operation. Okay, let me skip this slide. This is some demonstration of quantum dot lasers grown on a silicon substrate. So silicon, you know, is a very attractive material for microelectronics and consider it as a promising platform for optoelectronic as well, because this could provide a combination of microelectronic transistors or so on with optical elements to manipulate with light, to provide information and data exchange between different chips, maybe inside chips using light. But silicon is a material which cannot emit light because of indirect band gap structure. So one possible solution is to grow 3-5 materials on a silicon substrate, and this approach requires very careful optimization of epitaxial growth because of silicon and 3-5, for example, gallium arsenide, are very different materials, different in lattice parameter, different in thermal expansion coefficient, and different in polarity. For example, silicon is just silicon, and the gallium arsenide contains both gallium and arsenic. And the epitaxial growth of gallium arsenide on silicon can be started from gallium atoms or from arsenic atoms, and when these two domains reach each other, the sort of crystalline defects appears. So nevertheless, because of certain tricks in epitaxial growth, it is possible to reduce the density of defects in gallium arsenide grown on silicon to the level of maybe below 1 million dislocation per square centimeter. Just to compare the quality of laser-grade substrate, pure native gallium arsenide substrate is below 100 dislocation per square centimeter. So the difference is 4 orders of magnitude. But nevertheless, quantum dots grown on this defective buffer can operate in lasing regime even at elevated temperature. Here is I summarize when non-sensitivity of quantum dots against different defects can be useful. For example, in Fabry-Perot lasers or in DFB lasers grown on a native gallium arsenide substrates, there are no sidewall defects and no crystalline defects because of epitaxial process. Because process is just growth of gallium arsenide on gallium arsenide, and no more new defects appears. But if, as I said, the structure is grown on silicon, lots of epitaxial defects appears, and quantum dots, because of their non-sensitivity to defects, provide suitable material quality for Fabry-Perot lasers on silicon. Another sorts of structures when defects are important is micro lasers. For example, micro disc lasers or micro ring lasers, because the size of such lasers are comparable to light wavelengths, or maybe tens micrometers or so. And in this case, the surface plays very important roles compared to conventional Fabry-Perot lasers. And in this case, quantums also give rise to very promising characteristics because of their stability against side-Wöhler combination. And finally, the most difficult case when micro ring or micro disc lasers are fabricated from the structure grown on a silicon. In this case, we have two sorts of defects: surface defects and epitaxial defects. And I will try to demonstrate in the last few minutes some achievements in these fields. So let me skip this slide because they demonstrate different sorts of micro lasers, and most of them are quite complicated structure, complicated in terms of epitaxial growth or complicated in terms of post-growth processing. So maybe the simplest one is micro disc lasers, which operates because of so-called whispering gallery modes, which can be considered like light reflection from the side walls. And because of total internal reflection, the quality optical quality could be very high, even if the size of this resonator are few microns. So it's like this slide shows like how microdisc lasers look like. The advantage is that we can use the epitaxial structures similar to Fabry-Perot lasers, no additional thick distributed Berkeley reflectors or some oxidation layers are required compared to, for example, vertical cavity surface emitting laser. The thickness of the epitaxial structure is quite small, and this provides good thermal conductivity, low thermal resistance, for example, and also low electrical conductivity. Well, this is another example where array of quantum dot microdisc lasers are fabricated on a silicon substrate. In addition to fabrication of monolithically integrated with silicon lasers, we can just transfer pre-fabricated microdisc or array of microdisc lasers grown on a native gallium arsenide substrate and then transfer this array onto silicon. This process is quite simple and can be compared with, for example, usual flip chip bonding with some modification, and this provides a flexibility of fabricating lasers, and the laser can be pre-tested before transferring on silicon, and also we have no problem with defect associated with epitaxial growth. Important things how to extract light from microdisc lasers, because the disc has a circular shape and usually light is distributed in the whole free space. So there are some methods how to make the light emission directive. For example, this half disc of half-ring lasers, but most suitable for optoelectronic application, for integration circuits, is just make evanescent coupling between, for example, planar waveguide and microdisc or micro-ring laser, like is shown here. But also there are methods to extract light from microdisc laser using so-called radial coupling. And finally, okay, few last minutes about some properties of these microdisc lasers. For example, they also can operate at elevated temperature, more than 100 degrees C. For sure, the maximum operation temperature depends on the size. The smaller the size, the lower the operation temperature. Important parameter is modulation efficiency, so how fast the laser can modulate light, because this directly restrict the maximum bit rate which can be achieved using a laser. And for the moment, the maximum modulation frequency is roughly 8 gigahertz, and we succeed with optical fiber transmission, data transmission with a bit rate of 10 gigabit per second without any temperature stabilization or cooling of the laser. It is also important for integration. Also, not only lasers, but also photodetectors can be fabricated from the same epitaxial wafer. So the operation regime, lasing or detecting, depends just on polarity of voltage applied to the structure. So the forward voltage provides gain and light emission, reverse voltage provides light detection. It's very convenient because two different elements can be fabricated from the same structure. What is also important, the quantum dots provide not only low threshold current density, but also very low dark current density. It's maybe the record low threshold dark current density belongs to quantum dot. The density of dark current is typically of few microamps per square centimeter. This corresponds to the level of absolute dark current is several tens of picoamps typically. And let me skip these slides because here is talking about some special sort of quantum dots which can be fabricated not by Stransky-Krastanov growth mode, but using different, a little bit different principle because of using slightly misoriented substrate. And let me come to conclusion. So I tried to demonstrate in this presentation the microdisk lasers are quite simple but powerful. So we can combine conventional laser heterostructure and very simple post-growth process and have some advantages in terms of size of lasers, in terms of their combination with different materials, for example, with silicon and so on and so on. So quantum dots are the very important thing for microdisk lasers, because quantum dots provides flexibility in wavelengths of operation, provides non-sensitivity to different sources of defects, and very high stability against, for example, temperature increase. And because of this, and maybe because of some other reasons, which is far from my field and not presented in this talk, quantum dot microlasers are competitive solution, for example, for short-range optical communication compatible with silicon-based components, not only electronic components, but also photonic components like modulators, waveguides, and so on and so on. So thank you very much for your attention.
Thank you for a very informative and amazing talk. Now, some questions? If not, I have one question. I think that the micro lasers that you presented in your talk may be in their demand in, for example, medical field. So, are they now commercially available?
Not yet. So quantum dot lasers of conventional design, like Fabry-Perot lasers or distributed Berkeley refractor lasers, really commercially available. At least I know two companies, one in Germany and one in Japan, which provide quantum dot lasers on market. One is founded by Russians, by Nikolai Ledentsov. Probably someone knows these guys at the company in Germany. And another one in Japan, founded by Professor Arakawa from Tokyo University, who was one of the pioneers of quantum dot laser activity in the world. So in these lasers indeed are also used for some medical application, for aesthetic application, for example, for hair removal, for some surgical, and I'm not very familiar with medical application. I know that, for example, one very promising application is optical coherence tomography for eyes and for some other tissues.
Yeah, sure. When you need a really broad band.
Yes, you're right. Yes, broad and which can be the wavelengths can be changed very rapidly. Yes.
Okay. Some other questions? Yes, please.
First of all, thank you very much for beautiful presentation. And my question about communication with laser disc. What is the experience for free space or for waveguides?
Yeah. I see. So when for free space communication is for sure quantum dot lasers have very little advantages. If we are talking about very long distances, so probably the most important parameter are angle of the divergence of light emission, the power, because light should be transmitted in a very long distance. And in view of this, I guess the preferable solution could be fiber lasers with diode pumping, because the efficiency is relatively high, because the power conversion efficiency of diode lasers can be in excess of 50%, and they can be very efficiently pump the fiber lasers, and the fiber provides very high power. So practically, it depends, of course, of the weight and size of the fiber lasers, but it can be changed from 100 watts to several tens of kilowatts. So it's very huge power, which is enough, for example, to cut some steel, to do some other constructive or destructive job. When we are talking about fiber communication, yes, in this case, quantum dots have certain advantages. For example, for 1.3 micrometer, there are two possible solutions. One is more traditional indium phosphide lasers with quantum wells, and another is a new one, quantum dots on a gallium arsenide. Compared to indium phosphide, quantum dots are more stable against temperature and have lower operation currents, and as I try to demonstrate, can reach more narrow line widths. So I think quantum dot laser has very good promises for this sort of application, and already start to use this. But for fiber communication, when we are talking about distance, maybe meters or 100 meters, like in data centers, no need in micro lasers, because conventional VCSEL or even edge-emitting DFB lasers have more advantages. Not necessary to make the laser small when distance are 100 meters or 100 kilometers. No reason. The only reason when small size of laser doesn't matter, quantum dot or other sort of laser are required, is when we are talking about optical communication inside chip, for example, or between chips, between inside some object which is small itself. So, for example, we can imagine, and all the history demonstrates that optical communication makes from huge distances to smaller and smaller distances. And now optical communication is widely used in data center when the distance not 100 kilometers but 100 meters. And we can imagine that optical communication will be used in computer, in cell phones, in some other optoelectronic and microelectronic devices. In this case, many lasers should be used by a single user. This is not the case of long-distance communication when many users use one laser. If so, the laser should be very cheap, because you should pay, one user should pay for tens or maybe 1,000 lasers. If it's cheap, other principles of device fabrication should be used compared to very high quality, very high level lasers, but if we are talking about consumers electronics, the quality could be medium, but the most important thing is simplicity of fabrication, low price, and so on. So in this case, microdisc lasers has many advantages because the Getter structure is very simple, no Bragg reflectors are required, the epitaxial growths are very simple. There is not need to reach very high precision in, for example, thicknesses of any layers, no external oxidation of layers. Everything is very simple, just etching and nothing more. And in this case, quantum dots again have advantage because they are very stable against shrinking the size of a laser. I don't think that quantum dot microdisc laser is the best solution because of, as I said, we need to have a directivity of emission. So maybe some modification of the cavity will be invented, or maybe already now invented, but not in the production. But for sure, quantum dots have advantages in the active region because they, as I said, very stable against temperature. And you know that the laser should operate at elevated temperature because electronics typically increase the ambient temperature. So in data centers, the temperature are separated into zones. There are zones where personnel can stay, and a zone where personnel cannot stay because of temperature is too high. But laser should operate even there. And because of stability against defects, as I said, and also because of compatibility with the silicon. So quantum dots demonstrate, and the only active region which operate with reasonable parameters when the wave is grown exactly on the silicon, So because the quantum wells unfortunately cannot operate, because very sensitive to defects, because electrons can move along the quantum well plane. So sorry for my long answer to your question.
Thank you very much for details.
Let's thank the speaker one more time.
Yeah, thank you.
And now we have time for a short coffee break.